Hello and welcome to today's video. In this video we're going to talk about polar curves. The idea here is to define a function in terms of the angle of a point. So we're looking at a point given in polar coordinates. We want a function that turns an angle into a radius so that the result is again given in polar coordinates. The curves that we generate this way will be called polar curves, and they sometimes play a specifically important role. We're also going to talk about how to compute the area covered by such a curve between certain angle values. So the video is called Polar Curves. And as I said, it's sometimes convenient to define a function using polar coordinates. So that's what we want to do. We want to define functions using polar coordinates in the plane. And we are going to restrict that discussion to the two-dimensional planes. We're going to talk about planar curves only. Of course, similar things can be done in higher dimensions as well, but we're not going to discuss this generalization. So what we'll usually do is we'll use the angle as the domain of our function, and then the function value will be interpreted as the radius that is connected, associated to that angle. And we'll usually use the notation the radius r is given as a function of the angle phi. So we write something like r of phi for the radius. And that also means the domain is usually restricted to 0 to 2 pi or a suitable subset, or of course any suitably translated version of that. There's usually a restriction on the admissible input, which means you can do a full rotation, but not more and maybe less than that. So usually the domain is a subset of the set 0 to 2 pi, or a suitably translated version of that. And just as a quick reminder, recall we've talked about polar coordinates, and we've talked about the transformation from polar coordinates to Cartesian coordinates. We'll denote that as T, transformation, in this video here. So given the inputs r and phi that define a point in polar coordinates, the transformation computes the corresponding Cartesian coordinates, and those are given as r times the cosine of phi and r times the sine of phi. And strictly speaking, the radius should be greater or equal to 0. Of course, you may also use negative radii, which simply means there's a reflection at the origin. So basically that corresponds to the angle that is shifted by pi, right? But that's more of a technicality. So let's define what we mean by polar curves. So what we want is an interval somewhere between 0 and 2 pi for the angle, and again translated versions of that, restricted versions of that will also do, but for the technical definition we'll use this interval here. So let I be an interval between 0 and 2 pi, and let r be a function on that interval, that assigns to each angle a value that is greater or equal to 0, the radius. And usually you want that to be a continuous function. In many cases, we'd also want that to be differentiable, but for the definition, continuity is fine. And then we can define a curve based on that. That will be a curve defined on the input set I, so the angle will act as the input to that curve, and the curve will live in the plane R2. And that curve is defined by gamma of an angle phi is the point in Cartesian coordinates that you get by applying this transformation from polar to Cartesian coordinates to the point given as r of phi and phi. So we use phi as the angle and r of phi as the radius. And this is the polar curve associated to that function here. And again, t is a transformation from polar to Cartesian coordinates. Usually, to denote such a curve, we'll simply use the notation r equals r of phi, so we'll just define the function r and implicitly mean to define that curve. So usually a polar curve is given by means of defining the function r. Let's have a quick look at a few examples. First, and probably easiest example you could think of is, of course, the circle. A circle with a given fixed radius is, of course, a polar curve. To each angle, you can associate a radius, and the radius is simply constant. And the curve that you get is the circle, depending on the angles that you use for your domain. It might either be the full circle or part of it. So, a circle with radius, let's call that r star, that's a fixed value. Is a polar curve. And for example, it can be represented as the polar curve gamma from 0 to 2 pi, given as gamma of phi equals radius times cosine of phi, radius times sine of phi. So that's simply saying we have t of r and phi, and of course that r is the fixed radius now, so I'll use an r star here. Or you could simply say we specify this as r equals r of phi is simply defined as being the constant r star. So what does a curve look like? A quick sketch. So to every angle, we associate the same radius And that means basically what we get is a circle like that, right? So here is our star, and that radius is the same everywhere along that circle here. Another possible example for a polar curve that looks a little more interesting is the so-called rose petal curve. And that is given as radius of phi equals 3 times sine of 2 phi. That's also a polar curve. For each phi, you get an associated radius, and this time the radius changes a little. And what does that look like? Well, if we start with phi at 0, so we want to have phi between 0 and let's say pi over 2. So the first point that we get is for phi equals 0, then we get sine of 0 is 0. So the starting point here is obviously the origin. Then the radius starts to grow up to the point where the sine, the argument of the sine, becomes pi over 2. And as the argument is 2 phi, that happens when the argument becomes pi over 4. So when the phi becomes pi over 4. So there it starts to grow up to that point, and then it starts to decrease again up to the point where the argument becomes pi, and that happens when phi hits that point pi over 2. Then we'll have another root of the sine, and that means the radius goes back to 0. So basically, what that graph looks like is the radius first increases with increasing angle up to a certain point, then it turns around, and then it decreases again. And that's where the name rose petal curve comes from. So it's part of a petal of a flower. And if you draw the same curves for the other parts of the plane, those would look something like that here, right? So you get a flower if you draw all of those 4 parts here. Now, those are examples of polar curves. And now, what we'd also like to do in this section is we want to determine the area of a sector of such a polar curve. So that's going to be the goal of the last part of this video. We want to determine the area of a sector of a polar curve. Now, how do we do that? Well, first we start with the simplest possible case. We start with a circle. That is simple because we know what the area of a circle is, and we know how to determine part of that. So imagine we have a circle that looks something like this here. And let's say we want to determine the area between 2 given angles. So that is the angle phi 1. That here is the angle phi 2. And what we'd like to do is we'd like to determine this area here. Or that sector. Now, what is that area? Well, we do know that the area of the whole circle is given by r squared times pi. So let's say we have a radius of r here. And then the circle area is given as r squared times pi. So that part here, that is the circle area, or the disk area if you want, of that whole circle. And now we need part of that, and well, what part do we have here? We have the part between the angles phi 1 and phi 2. And basically the difference of these angles corresponds to the length of that line, of that sector line here. And of course, the ratio of the whole area that we want is equal to the ratio of that length to the length of the whole circle line here. So that's the ratio that we need. And that means we just multiply this by phi 2 minus phi 1. That's the difference of angles. So that's the length of this line here. And we divide that by the length of the whole line. And the length of that whole line here, that is simply 2 pi. Right? So that is the ratio of the circle line for the segment as compared to the whole circle. And that's how we can compute the area that we want. Now to make this a little simpler, of course the pi here, that cancels out. So what we are left with is r squared over 2 times phi 2 minus phi 1. Now that's a simple case of a circle. Now what do we do in the more complicated case of a general polar curve? So let's say we have the general polar curve with radius r equals r of phi. So what does that look like? Let's make a quick sketch. So for example, imagine we have a curve that may look like this here, and maybe it continues. And we want the area between these two angles here. So that area is the one that we're interested in. And that here is the function r of phi. Now what can we do to compute that area? Well, you might remember that we defined integrals in the one-dimensional case in a similar fashion. You could see that as the graph of a function over a given interval. In this case, the difference is the interval is given by angles, not on the real line. What we did is we subdivided that interval into smaller and smaller parts, and we approximated the area through rectangles. And of course, we can do similar things here. So what we'll do is we'll take this thing here, and we'll subdivide that into smaller parts. So what we do is, instead of covering the whole sector, we divide that into several smaller parts here, and we approximate each of the areas in the smaller parts by a circle line. So something like this here. That's similar to the idea of one-dimensional integration, actually. So basically what we have here is, this is our, let's call it phi 1 tilde, and we have phi 2 tilde, and so on, up to some point. The last one we'll just call it phi n tilde, and of course we make this subdivision finer and finer until we are able to compute a limit here. So the idea is to use a subdivision of the angle space, of the angle interval. So we do subdivision of the angle interval, plus we do an approximation of each sector by a circular sector. And then what do we get? Well, the area that we want to compute is then approximately equal to a sum. Now for each sum, let's say we start at 1 and we sum up to n minus 1, so we always consider the left part of our interval for the subdivision, and let's say we approximate each of those sectors by the radius on the left. So we use phi I tilde and the radius given at that point over 2. You can take the square of that radius, of course, and then we multiply that by the length, so to say, of that interval here, so by phi I plus 1 tilde minus phi I. Right, so we just use that formula here, and in place of a constant fixed radius, we use a radius of one side of our subdivision. And of course, the result will change if we use the other side of the subdivision, but as we're going to make these subdivisions smaller and smaller anyway, it doesn't really matter. Basically what we have here is a Riemannian sum. So that's same thing as we have for one-dimensional integrations. And that means if we now take the limit for a subdivision that becomes finer and finer, and I'm not going to exactly define what that means, it's all analogous to what we did in one-dimensional integration, then what happens is that sum will turn into an integral. So what we do is we take the limit for infinitely fine subdivisions. So we subdivide that into infinitely many parts and such that the single intervals become smaller and smaller in that subdivision. And then what we get is a formula for that area. And that is then the integral between our two boundary points, phi 1 and phi 2. So this here is phi 1, and this here is what we call phi 2. Same here, phi 1, phi 2. And we integrate over r of phi squared over 2 d phi. Right, so basically this here, this distance here, that becomes finer and finer in the limit that basically turns into this d phi element here. Okay? So this is where the integral comes from, roughly, without going into too many details. And that's the formula for the sector area covered by a polar curve between the two angles phi 1 and phi 2. Now, of course, that prompts the question, can we also do that by curves that are not given as polar curves directly? Can we apply that formula for a curve given in Cartesian coordinates? And of course we can do that. And how we'll do that will be one of the topics of the upcoming videos. As usual, I'll see you then.